I've been talking about relativity, one of my favorite subjects in physics and in science, and a moment ago in a previous video I talked about how to use space-time diagrams to represent the motion of an observer through space and time, and if you're using this special hyperbola graph paper, which I learned of from my colleague Tom Moore at Pomona College, if you use this special hyperbola graph paper, you can even do some calculations directly on the graph paper. What I want to do right now is talk about one additional thing about space-time diagrams using this paper and using this technique of getting quantitative data off of these pictures. I want to talk about this and talk about different observers' perception of time. Namely, how do you understand all the events that Zach, who is moving at speed 2/3 light years per year, 2/3 the speed of light through space and time, what are all the events that Zach believes occur at time equals 0? Remember, this is a non-trivial question because in relativity, different observers disagree on concepts like space and time. What is this interval of time? What is an interval of distance? So we need to be able to come up with something that everyone can agree on in relativity that will give us a defining concept of when some event, some point in space and time, occurs at that observer's perception of time equals 0. To begin with, I want to refer back not to this graph that I'm drawing for Zach, but rather I want to talk about Alice, who is an observer sitting still at x equals 0 in the graph's reference frame. And I want to come up with a technique that Alice can use to say, aha, there is an event that took place at time equals 0. Here's the trick. Every observer in relativity agrees that light travels at the same speed, 1 light year per year. No matter who you are, you agree on that. That's one of the fundamental things about relativity. So we're going to use the light, and in particular almost a sort of radar pulses sent out by Alice or by Zach. We're going to use light as our way of defining which events happen at a particular time. Here's the idea. Imagine, if you will, that Alice sends out a radar pulse, something moving at the speed of light, at time equals -2 years, or -2 whatever the heck units, as long as they're units here and light units here, so seconds and light seconds, years and light years, whatever. At time equals -2 light year, or -2 years rather, light years comes in a second. Alice sends out a radar pulse. We know that would go at a 45-degree angle on the graph because that's the direction that light always goes. And let's say that at time equals +2 years, Alice receives a reflection of that radar pulse that reflected off of something at a particular event. And again, reflection will be, it's light, it's moving, it's coming in at 45-degree angle again. Must be coming in at that 45-degree angle. If Alice observes those things, that reflection, well, light moves at a constant speed. If it goes out and bounces and comes back, it must have bounced at exactly the middle. So in particular, if I follow this light radar pulse going outward and follow this one coming inward, they must meet at the point where the reflection happened. And because light travels at 1 light year per year, if it took 2 years to go out and 2 years to come back, it must have reflected off of something 2 light years distant. So this also defines Alice's idea of distance, by the way. So Alice knows that if she sent a pulse at time equals -2 and it came back at time equals +2, the reflection itself must have happened at time 0. Similarly, if she did send out a pulse at time equals -1 and it came back at time +1, that reflection must have happened at time 0. If she sent out a pulse at time equals -4 and it came back at time +4, that must have happened at time 0, as understood by Alice. So by doing this, you could imagine me doing this over and over and over. The origin is obviously a time equals 0 point. And then I can draw a line through all those points. And that's Alice's perception of time equals 0. Thus far, this is the most boring way of drawing the x-axis you've ever seen in your life. Let's apply it to Zach. Zach is traveling at speed 2/3 speed of light. Zach's traveling at 2/3 the speed of light, and so we're going to have Zach send things out at different times along the way. Technically, I should be having Zach send things out at Zach's time -1 year and Zach's time and receiving it at Zach's time +1 year, you remember Zach thinks 1 year has passed when his path in the space-time diagram crosses this first hyperbola. And 1 year before the origin would have been when this path crossed that hyperbola down there, 2 years before, 3 years before. That's how we count time for Zach. For convenience in drawing this, and because it doesn't matter, I could have done the same thing for time equals -2.73 years if the reflection came back at time equals +2.73 years. For convenience, I'm going to choose times where Zach's path intersects with nice grid lines on here. So, for example, speed 2/3 c means that at time, Alice's time, -3 years, position -2 light years, Zach's path happens to be an easy place to read on this grid. So I'm going to be lazy and use that. So let's imagine that at that particular moment, -3 years as seen by Alice, Zach sends out a flash of light, a radar pulse or something. Remember, it goes at a 45-degree angle in here. So I'm supposed to take this point and I'm supposed to extrapolate up along a 45-degree angle. Okay, so that's the pulse. This dashed line is the pulse of light that Zach has sent out. And I'm going to assume that Zach receives this pulse of light at, just as I did here, at +3 years as seen by Alice. Now again, that's going to be some fraction for as seen by Zach. It's going to be about 2 1/4 maybe years as seen by Zach. But as long as it's equal on both sides, it'll come out to be 0 at the midpoint, right? So here is +3 years as seen by Zach. I don't hardly even need this ruler to do this, the meter stick. I can do a 45-degree angle for one box pretty nicely. So having done that, what I can see is Zach sees this light go forward from here, bounce, and come back to Zach. So the point where it bounced, right here, must be a point that Zach believes is at time equals 0, because it's equally spaced between the light going out and the light coming back to Zach. Let's do another one. -6 years for Zach seems like a pretty appealing thing to put in here. -6 years, well, -6 years is seen by Alice, so Zach's, that's going to be 4 1/3 or something, 4 1/2, something like that, years. I'm going to draw, again, a 45-degree angle going up from there, and we'll see what we come up with. Here's this point. I want to make sure I get the right line here. I hope this is right. Yeah, it looks right. So if Zach sends out his radar pulse around here somewhere, all right, and then it reflects and it comes back and reaches him at time equals 6 as seen by Alice. Again, time equals -6 as seen by Alice, time equals +6 as seen by Alice, whatever it is for Zach, reaches him here. Let me extrapolate this backward from his path back to where it would have come from. Again, okay, my line's not quite perfect at the corner, but that's going to be at this point. That's another point that Zach will consider to be time equals 0 in Zach's perception of time. So let's start connecting the dots, because this is going to be another straight line. Sorry for all the dashed lines going on here. It's going to be a little tricky. I will try to do something a little bit straightforward here. Let's look at what we have, what this angle winds up being, and see what we can draw here. Line it up nicely. I said line it up nicely. Okay. Well, it's not perfect. Okay, the big dashed line that I just drew, maybe I should be strengthening it somehow. This big dashed line that I've just drawn, this is Zach's time slice. This is a time slice as seen by someone going 2/3 c. 2/3 the speed of light, it reflects all the points that are t equals 0, that look like time equals 0, to someone traveling at the speed of light. So this is, I'll label, for t equals 0, that's supposed to be a 0, for v equals 2/3 c. That's, I call it a time slice because if Zach were to make a slice through all of time and say these are the things that happened at time equals 0, that would be what he would say was time equals 0. This is one of the weirdest things about relativity, that different observers disagree on the order of events, on what events happen at the same moment. So for example, Alice would say that if something compared to Zach passing by at time equals 0, Alice would say that this event over here, their friend Murray has a birthday party, Alice would say that that happened 2 years after Zach passed by Alice at the origin. Zach would say that Murray's birthday party took place, well, I need to count upward, but several years before he passed Alice at the origin. The trick is that for events that take place widely spaced in space, in distance, different observers will disagree on what came first and what is simultaneous and what isn't. There's a lot I could say about this, but the neat thing about this diagram, I won't say everything about relativity right now, the neat thing about this diagram to notice is the following. The slope of this line, this dashed line representing Zach's perception of simultaneity, the slope of that line is exactly the inverse of the slope of Zach's path on here. Namely, whatever angle, this is Zach's path at a slope of 3/2, 3 years up for every 2 light years over. This dashed line, look at it, 3 light years over, 2 years up, 3 light years over for 2 years up. It's exactly the inverse of the slope. Another way of thinking about it is whatever angle you measure down from vertical here has to be the same angle that you measure up from horizontal here. So someone at rest, Alice observing at rest, her path goes straight up. Her time slices are just the graph time slices like this. As you go faster and faster, your slope gets flatter, faster is flatter, and your time slices tilt upward as they go closer and closer to 45 degrees. That's what's going on with faster and faster motion. And so you don't need to do these calculations every time. You don't need to do this construction, this crazy bouncing light thing. You just need to know time slices for an observer moving close to the speed of light are tilted on a space-time diagram by the same angle that their path was tilted down. That's the idea of simultaneity in relativity. Maybe I'll toss out one other useful fact. Useful fact number one, I guess, the one other useful fact I'll throw out there is if you've drawn a time slice that goes through the origin, the time equals 0 time slice, you can follow that time slice and watch it cross hyperbolas. Here it crosses one, here another, here another, here another, here another. You can see where it crosses those hyperbolas on this graph paper. Because that's the time equals 0 time slice, delta t squared is 0. And what you're going to find then, if all observers agree on delta s squared, and the delta t squared is 0, the distance along that time equals 0 time slice is measured by how many hyperbolas you cross. In the same way that the time along Zach's path is measured by how many hyperbolas he crossed. So if I want to know what is the distance to, say, this event here, this second reflection that looks like the reflection of the light of the radar pulse that Zach sent out at time equals -6 years from Alice's point of view, that came back at positive 6 years from Alice's point of view. Well, we can see in the graph that Alice would say that happened at time equals 4 years and distance 6 light years. That's the position that Alice would assign to it. Well, here's the trick. Zach would say that that happened at time equals 0. That's the whole point, time equals 0. But Zach would also say, let's count a little. Let's count hyperbolas. It's 0 light years, 1 light year, 2 light years, 3 light years, 4 light years, looks like about, here's 5 light years, looks like about 4 1/3 light years away. something like that. So I can count that up. He would say that's 4 1/3 light years as opposed to Alice's 6. Or for that matter, you could just extrapolate downward between these two hyperbolas. It's right between the 4 and the 5 labels. If you follow the hyperbola down to the axis, and if you look at it, it'll extrapolate to about 4 1/3. So that is the way that you can use the time equals 0 time slice to understand a moving observer's perception of position and not just the moving observer's perception of time. I hope that gives a sense of the fact that these space-time diagrams can capture a whole lot of information. With later examples, we'll talk about how to do calculations that aren't along this path or that path. It's always a two-step process. But for now, that gives a sense of where those paths come from.